A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. This is my 13th lecture about the course of thermodynamics, having the course code of PHY331. In today's lecture, I will discuss dielectric slab, paramagnetic rod, and at the end, I will discuss intensive and extensive coordinates. The basic objective from today's lecture is the understanding of the dielectric slab. Moreover, we need to develop the equation of state at equilibrium position for the dielectric slab. Similarly, we need to know the paramagnetic rod and develop the equation of state for the paramagnetic rod, and at the end we will discuss the intensive and extensive coordinates. For understanding the dielectric slab and its thermodynamics interpretation, we need to consider a parallel conducting plates capacitor. Here this is a parallel conducting plates capacitor in which two plates which are parallel to each other, they are separated by a distance L, and the area of each plate is represented by A. So the region in between the two plates is filled with an isotropic solid or liquid dielectric. So we will consider this region to be as a dielectric slab and understand its behavior upon charging and discharging. So a constant voltage is applied across the plate, and as a result of this constant potential difference, an electric field is created in the dielectric materials. In between the plates, the electric field is developed. So if we consider the molecule of the dielectric, and initially when there is no electric field applied on the dielectric, then it is in non-polar states. I mean, the center of the positive charge and the center of the negative charge are at single point, so it's non-polar. When an external electric field is applied, then as a result of this field, the center of the negative charge moves from the center of the positive charge, and a dipole moment is created. I mean, the center of positive charge is located at some distance from the center of negative charge. So we have different type of molecules. This may be polar molecule or non-polar molecules, but anyhow, so some are natural polar molecule and some are non-polar. But anyhow, when we external electric field is applied, the center of positive charge moves from the center of negative charge moves from the center of positive charge, and as a result a dipole moment is created. So this is a type of induced dipole moment. When we remove the external electric field, again the center of positive charge, negative charge come back to this coincide at the center of positive charge, and there is no net dipole moment in that case. So if you want to find out the polarization in this case, then it can be measured. It is actually the degree of the molecule orientation in the direction of field, and it actually depends upon the electric charge induced on either phase of the dielectric material multiplied by the thickness of the dielectric, and it is known as a electric dipole moment per unit volume, and the electric dipole moment per unit volume is called as a polarization. So if we see the direction of the polarization, then it is always it is uniform and it is perpendicular. Here in this case it will be perpendicular to the plates, so it means the angle between the angle between them is equal to 90 degree. So how we can describe this polarization? The electric displacement is given by, that is represented by D, that is equal to D is equal to epsilon epsilon naught E plus P. Here epsilon naught is the permittivity of vacuum, that is actually a scalar quantity. E is the electric field applied, and P is the polarization. Here we discussed that is actually the polarization, dielectric polarization. So this is actually the equation for the electric displacement. To show the explicit dependence on volume, a new term is introduced that is called as total polarization, and there is some relationship between the total polarization and the dielectric polarization. That is actually the only polarization, because we want to clarify, or we want to introduce some coordinate that have explicit dependence on volume. So here we see that the relationship between the polarization and the total polarization is like that the polarization is equal to total polarization divided by the volume. So if we put this value, the value of P, I mean capital P, that is actually the polarization, over here in this equation for electric displacement, so what will happen, we can modify this equation. Here just put the value of D is equal to epsilon E plus, instead of P we can write this P and divided by V. So the equation will be like that, it will be D is equal to epsilon E plus P divided by V. So the total polarization depends upon some parameters, and some of the parameters are the nature of the dielectric material. I mean the total, it varies from different to different material, so it means the total polarization depends upon the nature of the dielectric material. And the second thing on which the total polarization depends, that is actually the temperature. And the third thing on which the total polarization depends, that is the volume of that particular dielectric materials. So how we can develop the equation of state for dielectric materials? So if we consider a dielectric material and it is placed inside the parallel plate capacitor, then it experiences no significant volume changes at constant atmospheric pressure. So therefore the thermodynamic coordinate, just like pressure and volume, remain constant at this temperature. So we can no more use the pressure and volume as a thermodynamic coordinate in this particular case, for the case of dielectric slab. So we need to introduce some new thermodynamic coordinate that can describe this particular systems. So three thermodynamic coordinates describe the dielectric slab. The first thing that depends on the polarization of the dielectric slab is the electric field E, and it is measured in the unit of volts per meter. The second thing which is considered to be thermodynamic coordinates to develop the equation of motion for the dielectric slab is the total polarization, and the total polarization are measured in coulomb meters. And the third thing, it is represented by P. And the third thing that describe the polarization are the property of the dielectric slab, that is actually the thermodynamic coordinate for the equation of state, that is the absolute temperature, and it is measured in Kelvin. So if we write the equation of motion for a dielectric slab, that is actually at the state of at equilibrium position. So the equation of state at temperature about 10 K for many dielectric is given as P divided by V, that is actually the capital P, that is equal to A plus B divided by T into E. So this is actually the equation of state, and keep in mind again this equation of state is developed and it is always written for the equilibrium configuration. So here we can consider that the A and B are a constant quantity. P, I mean the italic P, is a total polarization, V is the volume, and T is the temperature, and E is actually the electric field. So the other part of the lecture and the thermodynamic description of another system, that is the paramagnetic rod. Just like a dielectric slab we need to understand first, and then develop the equation of state for the paramagnetic rod. So paramagnetic rod, we have different type of magnetic material. Some are ferromagnetic material, and the ferromagnetic material have intrinsic magnetic moment, that is actually the permanent magnetic moment. These magnetic moments are randomly oriented when there is no electric field present on it, but when some external electric field is applied on it, this magnetic moment orient in the direction of field, and it is aligned, increasing strength of external magnetic field align the magnetic domain in the direction of field, and at the point that is called as the saturation magnetization, when all the magnetic moments align in the direction of field, there is no more increase in the magnitude of magnetization, and that is called as saturation magnetization. This phenomena is for ferromagnetic material, but unlike ferromagnetic material, we have some other material that is called as a paramagnetic material. The paramagnetic material have no permanent magnetism and have no hysteresis, is not observing some hysteresis loop like ferromagnetic material. So what happen when we apply an external electric field on it, apply external magnetic field on it, some induced magnetization is created in this, and this induced magnetization that is actually from the magnetic dipole moment that is aligned in the direction of external magnetic field, and the magnetic dipole moment per unit volume is called as the magnetization, that is represented by capital M, and the external magnetic field is called as magnetic field strength, that is represented by H. This H, the value of H is given by H, that is external magnetic field, that is equal to B divided by mu naught minus M. Here mu naught is the permeability of vacuum and B is the magnetic induction. So again, just like in case of dielectric material, dielectric slab, we develop some explicit thermodynamic coordinates. Here in this case we also need to develop some explicit thermodynamic coordinates so that it has some relationship with volume and it have dependency on volume. So for that purpose we need to develop a term or a coordinate that is called as a total magnetization, and it is represented by this small m, and this small m, the relationship between the magnetization and the total magnetization is like that capital M italic is equal to this small bigger m divided by V, that is actually the total magnetization divided by volume, or total magnetization per unit volume is called as the magnetization. So if we make such changes in M, so what we need to put this value of M is equal to small m divided by V over here in this equation. So what will happen, this equation will be modified like that the value of H will be equal to B divided by mu naught minus M divided by V. This is the new form of the equation of H, that is the magnetic field strength. So the next part is that we need to develop the equation of motion for this particular paramagnetic rod, and we need to develop the thermodynamic coordinate for that. Here if we consider this is a thin cylinder or the rod that is placed inside a current carrying solenoid, the current carrying solenoid is used to create the external magnetic field for creating induced dipole moment inside this paramagnetic material. So when experimental results shows that at constant pressure there is negligible volume changes. So again we can consider that the volume and pressures are kept constant. So these two parameters, or these two coordinate has a constant value, it's not considerably changed. So we need to develop some new coordinate or understand the new coordinate for this particular systems. So in this case, the new coordinate for the dielectric slab for the paramagnetic rod is, the first one is the magnetic field, that is the external magnetic field. It is represented by H, and it is measured as amperes per meters. Is actually the strength of external magnetic field. When we increase the strength of external magnetic field, the induced magnetic moments increases. And the other factor that describe the total magnetization of these that has been developed to develop the equation that has been developed for this particular case is the total magnetization. It is represented by small m, and it is measured in the unit of amperes meter square. It has the unit of ampere meter square, because it is actually equal to, this is equal to, bigger M is equal to m small m divided by v. So if you do the cross multiplication, this m will be equal to capital M multiplied by v. So we can get this equation and this unit for that particular system. And the third things that is used to describe this paramagnetic rod is the temperature. This is the third coordinate. So here we have mainly three coordinates to describe the paramagnetic rod. The first one is the magnetic field H, the second one is the total magnetization M, and the third one is the temperature of the material. So experiment confirms that magnetization of paramagnetic solid is a function of the ratio of magnetic intensity to the temperature. So it means this is actually the relationship, or it is the ratio of the magnetic intensity and the temperature. So the equation of state at low values of above mentioned ratio could be written as, so we can develop the equation of motion for this particular case for the paramagnetic rod that is at equilibrium position. That will be like that m will be equal to small m is equal to c into c. I mean this smaller c, that is actually the Curie constant, is multiplied by h divided by t. This is some relationship that is called as a Curie law. And c subscript the c in the subscript c is called as a Curie constant, and that describe this particular case, that how we can understand the total magnetization of a particular system. So this is the equation of state for the paramagnetic rod. Here we can develop the unit for the Curie constant, and the unit of Curie constant can be measured or can be developed like that unit of Cc is equal to the unit of we can put the unit of Cc into H. From this equation we can get the unit of Curie constant, and that can be equal to A into meter square divided by A divided by mk, that is equal to meter cube into k. That is actually the unit of the Curie constant. So this material or the paramagnetic material have very nice applications, and some material that have the electronic or nuclear paramagnetism, it is particularly used to achieve extremely low temperature. Actually it's not the part of our lecture for the discussion of the that how we can achieve the low temperature, but anyhow this have very interesting application, and anyhow when the time reaches we can discuss and elaborate wide range of application of paramagnetic materials. So the other part of the lecture is devoted to the intensive and extensive coordinate. This is almost the end of this chapter, where we develop the equation of state for different thermodynamic systems. So at the end it is necessary to know the intensive and extensive coordinate. We have different coordinates, some are intensive and some are extensive, and it depends upon the we need to know what is the difference between intensive and extensive coordinate. So for this purpose we need to consider as systems in equilibrium, and we need to divide it into two equal parts so that we can know what is the difference between intensive and extensive coordinate. So divide it into two equal parts, each having equal mass. So the properties of the system that remain unchanged for each half is called as intensive coordinates. If we consider some of the property of the system that remain unchanged for each half of the system is called as a intensive coordinate, and those properties that are held or that are divided into two are called as extensive coordinates. Just like for the first case, in case of an intensive coordinate, the temperature remain constant even for both the section of this system, that is in equilibrium, and even the pressure remains constant. So this means the temperature and pressures are the intensive coordinate. And the other things is the extensive coordinates are the mass, as the mass is divided into, because it depends upon the mass, so it's the extensive coordinate. So intensive coordinates such as pressure and temperature are independent of mass. It means it has no relation. It has, and then this intensive coordinates are independent of mass, but the extensive properties depends on mass. So here we can elaborate some of the extensive and intensive property and develop that how it can affect the properties of these systems. So this table elaborate some of the intensive and extensive coordinates. So for a particular system, so if we consider a hydrostatic system, in that case pressures is the intensive coordinate and the volume is the extensive coordinate. Similarly, for particular stretch wire, tension is the intensive coordinate and length is the extensive coordinate. For surfaces, as we discussed in the earlier classes, surface tension is intensive coordinate and area is extensive coordinate. For electrochemical cells, electromotive force is intensive coordinate and charge Z is extensive coordinate. And for dielectric slab that we had discussed today, that the electric field is the intensive coordinate and total polarization is the extensive coordinate. And similarly, at the end we discussed the paramagnetic rod. So in case of paramagnetic rod, the total magnetic field H is the intensive coordinate and the total magnetization is the intensive coordinate. So this is something about the dielectric slab and paramagnetic rod and intensive and extensive coordinate. This is almost the end of this chapter. We can move to the next chapter inshallah in next class. Thank you very much.